Hi and welcome back. Today we're going to look at section 8.4, which is on trigonometric equations. Two types basically, but a lot of different types within those two types. So we're going to first look at solving trig equations in linear form. Then we're going to move into multiple and compound angles, higher degree ones, and then approximating using your calculator, which I don't think we have any of those on this one, so we will kind of probably skip over that. I don't think there's any of those on the homework section. I'll go and double check that, but all the ones that I know on your final exam will be ones that you don't need your calculator for. So we're going to take this one off of the table, okay? All right, so if we look at the basic two types that you have, you're either going to be asked to find specific solutions. So they're going to give you a domain and you're going to find only the answers that are in that domain. So there'll be a finite number of solutions, right? There'll be 2, 1, maybe 3 or 4 solutions. Then you're going to be asked to find the general solutions. So a general solution means in periodic functions, which all of your trig functions are, you're going to get the same answer in infinitely many times. So there's a bunch of answers. So when you're asked to find the general solution, okay, you're going to do one of two things. If your solutions are directly across from each other, we'll talk about that soon, then you're going to only add pi n. And I'm going to change this because n just to me gets mixed up in the problem. And remember when we did our domain from the graphing, we used pi k. Remember we added k? So I'm going to change that to k only because it just stands out a little bit more. So if your solutions are directly across from each other, we're going to add pi k to your answer. And if the solutions are not directly across from each other, then you're going to add 2 pi k. Okay? So change those to k's. So here's an example of what that means. So if I asked you to find specific solutions, I'm going to give you the domain. If I don't give you a domain, it's understood to be a general solution. So we'll keep talking about that as we go through these problems. So here, we want to solve this equation, okay, for any values that where x equals that between 0 and 2 pi. Well, that's one rotation around the circle, right? So remember how you solve these. You want to solve for x. So to move the sign over to the other side, you would take the inverse. So x would equal to the inverse sign of square root of 3 over 2. So remember, what you're looking for is the angle that has a sign of that value, right? So it's already drawn out for you, but the two angles that have a sign of the square root of 3 over 2 are up here at 60 degrees, that's pi over 3, and then over here at 2 pi over 3. So those are the two angles that have that sign. The signs down here would be negative, so those are not solutions. All right, so that would be my answer, the finite number of them between 0 and 2 pi. However, if you look at the graph of the sine function, right, remember it goes on forever and ever and ever. These 2 points actually happen an infinite number of times. We'll hit them here, we'll hit them here, we'll hit them, a bunch of times. So look at where they are on the unit circle. They are not directly across from each other. Directly across from each other would mean one would be here and one would be here. That's directly across. Then you would only add pi k because you'd get one every 180 degrees. But when they're like this, in order to get another one here, I got to go around the circle one whole time. So that's why we do 2 pi k, because that's where the next one will be. And then the same thing here, we'll go around the circle 360 degrees, gets me to the next one of those. So if they're not directly across from each other on the unit circle, add 2 pi k. So this would be considered the general solutions of the same problem. Okay, so remember, if it's a specific solution, they will give you the domain. If they don't give you a domain, you would write your answers always like this. Okay, all right, so these go from kind of easy to a little bit harder. So we'll go through and work these, and hopefully this will be enough to help you with your homework. All right, so we'll notice the first 2 on this page are asking us for specific answers between 0 and 2 pi. And then the bottom one on this page just says solve the equation. Now I wrote general solution so you know that, but typically that would not be there, okay? All right, so let's start. So remember, to solve any equation, you're going to work yourself from the farthest thing away from x and work yourself in. So the first thing we're going to do is subtract 5 from both sides. So 4 minus 5 is -1. Then we'll get rid of that square root of 2, so we will divide both sides by the square root of 2. Okay, if you know that, otherwise we're going to rationalize that, so that would be negative square root of 2 over 2. And then get rid of the cosine, so we'll take the inverse cosine. Okay, so again, we're looking on the unit circle, which angle has a cosine value of negative square root of 2 over 2. All right, so I've got the unit circle here to help, but just, you guys should know that. So where is the cosine negative? It's negative here at 3 pi over 4, and then it's also negative at 5 pi over 4, right? So those are the only two places on the unit circle where the cosine is negative square root of 2 over 2 in this interval right here. So our answers would be 3 pi over 4 and 5 pi over 4. And that's it. Now you're going to give your answers in radian form just to practice, because again, I know on the final they like for usually all the work is done in radians. Okay, now on Hawks, I don't know, it'll tell you whether to give your answer in degree form or radian. Okay, all right, so let's do the next one. Solving for theta, work your way from the farthest away and then work yourself closer to tangent. So first thing we're going to do is subtract 1, divide by the square root of 3. Now this one I'm not going to rationalize because it's easier to find this on your circle, leaving it that way. So remember, tangent is y over x. So tangent is negative in the second and the fourth quadrant. So y over x. So the tangent here would be 3 over square root of 3 over 1, so that's not right. So this is the angle I want. The tangent of this angle is 1 over negative square root of 3, which also means 11 pi over 6. That also has a tangent of -1 over the square root of 3. So there's your two specific answers, 5 pi over 6 and 11 pi over 6. So I didn't go my one step farther, got ahead of the game. Take the inverse tangent. Okay, so again, those angles, theta would, well, that was theta. First one was x. Like most of you guys, and I don't really care, but typically that's a theta, but when you're solving equations, a lot of times they make those x's. So just remember that's the angle, okay? So just heads up on that. All right, so we said we're going to get 5 pi over 6. That had a -1 over square root of 3 tangent, and 11 pi over 6, right? So those are your two answers for that one. All right, now this one, we're going to just solve. So not specific, so we're going to get an infinite number of solutions. All right, so I need to get all my cosecants together, so I'm going to subtract this cosecant over here. So 3 cosecant of x minus 1 cosecant of x will give me 2 cosecants of x. And I'm going to divide both sides by 2. And then take the inverse. Okay. So remember to look for the where is the cosecant on your unit circle equal to 2. I'm just going to put over here, that's the same as where the sine value is 1/2, right? That's the reciprocal of that. So these are easier to find on the unit circle. That's not on the unit circle, but that one is. So that's much easier. So we're looking for a positive 1/2 sine value. So remember, sine's positive above the x-axis, so that would be at pi over 6 and at 5 pi over 6. Down here, your signs are negative, right? So pi over 6 and 5 pi over 6. And I'm writing them separate because now I have to write the general solution. So look at pi over 6 and 5 pi over 6. Remember, they're not directly across from each other. Okay, to be directly across would be here, right? Straight line. 180 degrees away. So these are not 180 degrees away. So that means you're adding 2 pi k to each answer. So those are the general solutions. Okay? All right, let's look at the next page. These getting a little bit harder because now we're involving multiple or compound angles. So you'll notice now there's that double angle in here. Okay, so we have a little bit more to do. This one is a half angle, so a little bit trickier. Okay, so pay attention to the steps. The first two again are specific, and then the last one will be a general solution. Okay, so you're still solving the same way, but here's the catch. When you work from the outside in, you'll see what happens here. So the first thing I'm going to do is move the 5 over, which I get 8, right? 5 plus 3. Then the next thing I would do is divide by 8, get 1. Now, this is in the middle, so you're working yourself from the outside in. So the next thing you have to get rid of is the cotangent. You can't divide by 2 yet. So to get rid of the cotangent, I would take the inverse. Okay. So at this point, when you do these double and half angle ones, the first thing you're going to do is find the angles. So I need to go to the unit circle and find where the cotangent is equal to 1, positive 1. Well, tangent and cotangents are positive in the first and the third quadrant. So cotangent is 1 at your 45 degree angles. So pi over 4 and 5 pi over 4, right? So those are the same. Those are directly across from each other, but that's where you would equal, the cotangent would equal 1. All right, so I've got 2x equals pi over 4, and remember the other one was 5 pi over 4. But we still have this 2x here. So now, once you've got your angles, now you will divide both of these by 2. Okay, so that gives you pi over 8 and 5 pi over 8. And then these are your answers, which are not right across from each other. Oh, I'm sorry, these are specific. So those are the only two. I'm getting ahead of myself. All right, so those are the angles on the unit circle that have the cotangent of 1. I divided by 2. So I was getting ready to say if this was a general or specific solution, or the general solution, I would add 2 pi k here. Even though these are right across from each other, these are not. And the answers are the ones you're looking at. Okay? But that was just specific, so that was it. Jumped the gun on that one. All right, so let's look at the next one, which is half angle. Okay, so before I can get rid of this 2, I've got to get rid of the cosine. So I'm going to leave x over 2. To move the cosine over, I would take the inverse. And now I would go to the unit circle and find my angles where the cosine is positive square root of 3 over 2. Okay, I know that's in the first quadrant, which is pi over 6. And then way over in the fourth quadrant is the other one where I have a positive square root of 3 over 2. So that is 11 pi over 6. Now, I'm solving for x. So to get rid of the 2, I would multiply by 2, right? You've got to multiply by 2, not divide by 2. So I'm going to multiply each of these by 2. So that gives me x on the left. 2 pi over 6 is pi over 3. And 2 times 11 pi over 6 will be 11 pi over 3. Okay? Now, I may have to add more to this. I'm not sure. So where is 11 pi over 3? Or I might not have said that the wrong way. I might have to either add some or take some away. So remember, I only want answers between 0 and 2 pi. Well, if I write 2 pi as something over 3, that would be 6 pi over 3, right? That's 2 pi. So this is bigger than that. So that is not one of my answers. So you got to be careful. You always want to check, the answers that you know are on the unit circle, then that's fine. But if it's too big, then you got to take it out. So that tells me I got to go back up. So I'm thinking about the one that I just did. I might need to add one to here. So let's look at that. Okay. So 2 pi is, if I write it over 8, would be 16 pi over 8, right? All right, so remember, every 360 degrees I get another one, but if these are only so far apart, if I added another 2 pi k to this, that would be 16, so I'd get 17 pi over 8, which is bigger. So that would not be in, so I don't need any more in here, but I just wanted to check to make sure there was not one that would be in there, okay? All right, so that one was fine, just wanted to go back and double check. And this one of the answers was too big. It was not in this interval, okay? All right, the last one on this page doesn't give me an interval, so this is a general solution. So again, I got to get rid of secant first. That's the outside. So I'm going to leave the x minus pi over 4 and take the inverse secant. Okay, so remember, the inverse secant is the same thing as inverse cosine being 1/2. So these are on the unit circle. These would not be. So where on the unit circle is the cosine equal to 1/2? Okay, that's what we're looking for. So the cosine is 1/2 at pi over 3. Okay, and the other cosine, remember, is in the 4th quadrant, so that would be at 5 pi over 3. All right, now we're going to add pi over 4 to each of these. So I got to add pi over 4 to here, and then I got to add pi over 4 here. So I'm going to make all of these have a denominator of 12, right? Okay, so pi over 3, I'm going to multiply by 4, so that's 4 pi over 12, and I'm going to add 3 pi over 12, which is pi over 4. So that gives me 7 pi over 12 for that one. Okay, and then over here, 5 pi over 3, multiply that by 4, we get 20 pi over 12. Add pi over 4, which is 3 pi over 12, and that gives me 23 pi over 12. Now, 23 pi over 12 is not bigger than 24 pi over 12. So these are all in the first rotation. So, but that's really close to 2 pi, right? Okay, so are these right across from each other, or are they not? Okay. So they would have to be multiples of 7. So 7 would be 14, and then 21, and then 28. So that's not directly across from that. So I would take each one, and I would add 2 pi k. So those would be the general solutions for those. Okay. All right. Now, on the last page, we have higher degree, and we're going to do some identities on these. So there's all kinds that you might get. Okay, so you just got to kind of work with this. All right, so if we look at example 7, okay, this one is higher degree because it's cosine squared. So again, we're going to move things over in the order that we should. So the first thing is to add 1 to both sides. Then we're going to divide by 2. Now we need to get rid of the squared. So we're going to take the square root of both sides to undo that. Okay? So remember that cosine squared of x is really, that's what it really is. Okay? We just write it that way for the shortcut. So that's the outside thing, because some of you will say, why don't you take the inverse first, right? You don't square a word, that's no such thing. So you're squaring that whole value. We just write it that way for convenience sake. So we've got to undo the square by taking the square root. So when we take the square root of both sides, and don't forget it's plus or minus, so we end up with plus or minus the square root of 1/2, which remember is the square root of 2 over 2. So we need all 4 of these, right? All 4 of these. So get the cosine over now. So I'm looking for the angle, any angle on the unit circle where the cosine is positive or negative square root of 2 over 2. So those are all of your 45-degree angles, okay? So we would get pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. All of those are within this interval. All of those have cosine values of either positive square root of 2 over 2 or negative. Okay? So that one had a higher degree, the squared. So you end up with more answers because you're going to get plus or minus with those. All right, the next one is a factoring problem. So here's what I always say. When you see a trinomial, and number one, the words have to be the same. You can't have like sine squared and then cosine. That's coming up. So the first thing you want to look at are, do you have the same trig functions? As long as you do and you see 3 terms, it's most likely factorable, okay? So what I would tell you to do is get rid of the signs for a minute. So let's just write it as 2x squared plus 5x plus 3. And then I want you to factor that. So if I factored that into 2 binomials, remember the first terms have to give you 2x squared, the last 2 terms have to give you 3, and you got to get 5 in the middle. So the 3 would go here and the 1 would go here. So 3 times 1 is 3, and then when you do the outer and the inner, you get the 5x, right? Then once you do the factoring, now in place of x, you're going to put your sign again. So this would be 2 sine of x plus 3, and a sine of x plus 1. Okay? So use your, just get rid of the trig functions to help you factor. Now, just like always, to solve these, you set each factor equal to 0 and solve. So we got 2 problems to do. So set 2 sine x plus 3 equal to 0, and we're going to set the sine of x plus 1 equal to 0. All right, so this one, bring the 3 over, it's negative, divide by 2, negative 3 halves. Well, there is nothing on the unit circle where the sign value is bigger than 1 or less than negative 1, right? Those negative 1 and 1 are your biggest values. So this one has no solution. Okay, then we come over here, subtract 1, take the inverse. So where on the unit circle is the sign equal to negative 1? That's down at 270 degrees, right? 3 pi over 2. So that's the only answer for this one. Now I didn't take the inverse here. I skipped that step because I already saw that that was negative. So, I mean, you could have done x equals the inverse sine of negative 3 halves. But as soon as I saw this was smaller than negative 1, I knew there was no answer. Okay, remember your sign values, the range goes between negative 1 and 1, right? So that can't happen. All right, last 2. All right, this one, again, I see 3 terms, but notice how one is sine and one is cosine. So I can't factor that like I did this one, not yet. I have to have all of the same trig functions, okay? Otherwise it's not going to work. So I've got to make one of these the other one. So to me, it's easier to take the square term and make that a cosine versus it's hard to go from a small term, make it bigger. So I know, remember that the sine squared plus cosine squared equals 1, right? So if I move the cosine over, the sine squared is 1 minus cosine squared. So I'm going to substitute in 1 minus cosine squared for sine squared. So 2 is out front, then I'm going to replace it with 1 minus cosine squared. Here's the rest. Okay. And now I can kind of work this out. So I'm going to multiply the 2 through here. So that's 2 times 1 minus 2 times cosine minus 5 plus 5. Okay. Now I can add the 2 and the 5. So I end up with negative 2 cosine squared minus 5 plus 7. I'm getting there. Now I can factor, but I don't like to factor with your cosine squared being negative. So let's multiply everything by negative 1. So now I'll get 2 cosine squared plus 5 cosine minus 7. All right, now that I can factor. Okay, so I'm going to do this. I'm going to add another piece of paper here real quick so that I don't have to go down. You guys can stop and do the same thing if you need more paper. So now we're going to do what we did above. Change the cosine squares, or the cosines to just x. So 2x squared plus 5x minus 7, just to help me factor. So still 2x and x. I need 7, so 7 and 1. I just need to get a 5 in the middle. So I'm going to put the 7 here and the 1 here, because that's 7x and 2x, and 7 minus 2 is 5. So I need 1 plus, 1 minus, and I need a positive 5, so that looks right for factoring that. So now I'm going to add in my cosines back. So it's 2 cosine of x plus 7, cosine of x minus 1. Same thing's going to happen here when you set each term equal to 0. First one's not going to have an answer, right? Because when you move the 7 over and divide by 2, you can't have a cosine value that's less than -1. So that's a no solution again. And then the cosine of x minus 1 equals 0. That one will only give us one answer. So take the inverse cosine. Where on the unit circle is the cosine equal to 1? Now, let's be careful, because the cosine is equal to 1 over here, right? And that's 0, and it's also 2 pi, right? So, remember the question. We're only giving numbers between 0 and 2 pi. Include 0, don't include 2 pi. So the answer that I'm going to give for x would be just 0. Okay? That's between the intervals that I need. I do get 1 again at cosine for 2 pi, but that's not in the interval they asked for. Okay? All right. So that one took quite a few steps. All right, so I just didn't want to, I knew I was going to need more paper, so, okay. So very similar to the one we did before at example 8. The only difference is before you can factor, you got to have the same trig function. So I can't work with 2 separate or 2 different trig functions. There's no way to do those, so you always have to switch them to just one. Okay? All right, so hopefully you got that down. We'll do the last one. All right. So, solve this one. So we have sine and cosine, so I have to switch one of them around. So what I would do with this is I see that I have a double angle here, right? So I'm going to go ahead and do the formula for the sine of 2x, which is 2 sine x cosine x, right? That's the formula for double angle. Now I can take the cosine of x and divide both sides by that. So now I end up with the 2 sine of x equals 1. Right, they cancel, and that gave me 1. Now I can divide by 2. And now I take the inverse of both sides. So specifically between 0 and 2 pi, what angle has a sine of 1/2? Okay, so we're doing the sine, and sines are positive in the first and second quadrant. So x would equal 2 pi over 6 and 5 pi over 6, right? Those are where the sines are positive 1/2. And that's it. Okay? All right, so those are the kind of problems you're responsible for doing. So don't worry about the ones with the calculator, because like I said, those are not on your final, and I will make sure they're not part of your homework. Okay? All right, you guys get to work on these. Let me know if you have any problem. Work every day. Okay? You got to get this stuff down. All right, have a good one.